Okay, 61C, let's get going. Okay, let's see people trickle in a little bit. Okay, welcome everyone. So today we're going to do a journey a little bit one level below kind of where we were last time. So we started looking at sort of high-level languages like C, and we did some work there, explain how to sort of write simple programs, why C is sort of very close to the hardware, but not too close. And we still need to watch out how we do some things. In next few lectures, we're actually going one level below. So we're going to see what actually a tool called compiler creates as a sort of an intermediate language that is like super close to the hardware. It's actually sort of the language of the computer, but still kind of symbolic enough that humans can write in it. And Krista showed last time kind of the world's smallest chess program. Somebody was brave enough to sit down in that assembly language and actually code it up. And you will too in a few days once you see it's not too hard. So today we're going to go and look at this intermediate representation where we're going to have instructions or kind of the vocabulary of that's very, very tailored to the hardware that's inside the computer, like one-to-one kind of tailored. And then we're going to learn how to write basic program constructs and go from there. So it will look something like this instruction and some operands based on which we work to both do arithmetic, load stores, operate on data, etc. Later we're going to turn that into a whole bunch of bits, and that's kind of on this slide. It's kind of shown right here. These instructions will map one-to-one to these strings of bits that the computer actually understands. And assembler is kind of the program that will do that for us. So I got like the last lecture of this MIPS kind of saga is going to be what are these number formats that will take, let's say this LW, which is load word, and turn it into the string of bits. Okay. Now, the basic job of a CPU is obviously to just basically execute lots of instructions. And there's a little bit of a trade-off here in what we want to call an instruction. Obviously, we would like at the high level for the CPU to do some tasks for us. Go fetch water, or go do some larger chunk of computation so that we don't have to be bogged down with little details. Right? But essentially, that's a very complex thing for a CPU to do. So if we could break it down into a bunch of smaller tasks, some of these smaller tasks could be reusable across a bunch of things that we want that CPU to do. And if we can identify these very frequently used parts, we could try to build hardware that really efficiently, quickly, and with low energy implements these tasks. And that's really kind of what we would like to call an instruction. It would be something that a piece of hardware can do very frequently and very efficiently. And through the history, it's been a trade-off trying to figure out what is that granularity so that we can actually do that. Right? This collection of instructions, which is really the vocabulary of a computer, we call instruction set architecture. It's a little bit of an unfortunate name. If you call it like the vocabulary of the computer, then that may kind of reflect it. But this is really what it's called. And you've probably heard about a lot of these names already. ARM, for example, is probably one of the most popular CPU designs and has associated instruction set architecture. Obviously, people who are still kind of tied to laptops or personal computers, x86 is kind of the instruction set architecture there. Even people who have Macs are really running x86 because there's Intel CPUs inside. MIPS is actually one that we're going to be focusing on in this class. It's actually also really popular. It belongs to this RISC kind of movement that we're going to talk about a little bit in a few slides. RISC-V or RISC-V is actually something that is kind of the latest generation in that RISC instruction set, originated from Berkeley. Here, actually, people who are going to be at Bears, there will be in the afternoon, the Plaque in Soda Hall will be placed for RISC-1. That's kind of the first computer from Berkeley that sort of spun this whole RISC design principle that we're going to talk about. And there's a bunch of other kind of instruction sets like IBM, Motorola, Intel IA64 that are all different kinds of instruction set architectures addressing different domains. So if we take a look at what these architectures are throughout the history, I mentioned already there was this trend to kind of have the instruction capture a whole task. So in early machines like VAX, that's one of the computers sort of in the 70s, you had sort of a task, okay, go multiply the two polynomials. So that's not even like multiplying a few numbers. Polynomials could be whatever length. So it's a completely arbitrary, like very complex task. It can be broken down in many, many small pieces, but they sort of needed that kind of task being done, so they implemented that. And then they needed another task, they would add another complex instruction. So these sets would be called complex instruction set architectures. And sort of it got down to the point that people sort of the inefficiency in just adding more complex tasks and then yet adding more hardware to support it. The machines were really big and bloated. And so there was this whole movement in the 80s called RISC, which really stands for Reduced Instruction Set Computer. And what that really means is, again, recognize these small patterns that occur very, very frequently, and then just optimize the hardware to do that really fast. With that small footprint, the energy will also come to be very manageable, so you're going to get both energy efficiency and speed from that architecture. And then once you've identified these really small chunks, these tasks, let software create compositions of these tasks, of these small instructions, to build bigger and more complex things to do. So, and so as you'll see on kind of the MIPS example, which is one of the first RISC machines that came out, the instruction set kind of fits on one page. There's like that many. And the number of registers that we're going to use. So it's very, very manageable and simple, but you can do great things even today with them. Okay, so MIPS, as I said, was sort of one of the first semiconductor companies actually that went out and built one such processor and commercialized it. And actually we'll see they're popular even today. I'll show you some examples of that. Mostly in embedded space. And but, in this class, we're going to look at the MIPS architecture for its simplicity, because it's a really good example of these RISC principles, and assembly code is kind of easy to learn. A bunch of other follow-on classes, like CS152, 162, 164, will kind of rely on that. Some may kind of wonder, why is it that we're not looking at, let's say, x86? It's a very, very popular architecture. X86 sort of started like this complex instruction set, and then they were trying to chop it up and simplify it through microcode to try to get it to run faster. So it's nowadays somewhere in between. There's a lot of kind of bloat around it. And so for the first thing for you to learn the sort of the principles of it, it will be too much. And actually if you look at kind of the number of devices that run RISC-like instructions today, it basically outnumbers significantly the x86 platform. If you look at the latest ARM 64-bit architecture, it's kind of making a pivot even more closer to kind of the MIPS instruction style. So it's a very, very useful instruction set to learn. Now, one big change between kind of what C level that we've seen so far and what we're going to be using in RISC or in MIPS instruction set architecture is the fact that our variables will now be things that exist physically in the hardware, right? So we're going to call these registers, okay? And because this is a physical thing that sits on a processor, there's only a limited number of them. In C, I can just do any number, declare any number of variables, and the program will work. How it actually does it underneath, it doesn't matter. But here, if we write directly in MIPS, we only have 32 registers to work with, actually. So everything we do has to be done in that little sandbox of 32 registers. The reason for that is that we really want to keep the hardware simple, right? We're going to have these 32-bit registers, 32 of them, tailor the operations and craft the MIPS code to really fit there. And we'll see actually later how we can use much more data than these 32-bit registers. Right? Obviously, otherwise, MIPS wouldn't exist anymore. But you have to be very careful how you do it. Okay? And the benefit here really is that, if we have registers directly to, let's say, the arithmetic logic unit, which is the thing that crunches the numbers inside, we can get data to that unit very quickly. When I take this laser pointer, put it on the wall, that distance is 30, 40 clock cycles on the processor, just for this light to go from here and hit the wall. So you can now maybe get a perception of how important it is that the data is right next on a chip to that processing unit. Because electrons can't run faster than the speed of light. And so really physically for the electron to go out into the memory and come back, not to mention other processes that are happening there, it takes a lot of time. And you want that data that you want to use really right next to where it's being computed. Okay. So I mentioned already it's only a limited number of registers. We have them in hardware. We can't put an infinite number of them. So you have to really carefully design the code. You may wonder why exactly 32? Is 32 a magic number? Why not 8 or 16? It's sort of like a Goldilocks problem. Today's machines actually use, so 64-bit architecture uses more than 32 registers, and they're more than 32 bits. Turns out you can actually get a speed up with modern processes because you can fit these more than 32 registers kind of close to that, actually several arithmetic units, and still get good improvements. But it's sort of like a Goldilocks problem. If you do 1,000 registers, you will be all over the place in the chip, and you won't be able to get very quickly to these registers and come back. Right? So at the time MIPS started, at least the 32-bit architecture, they picked 32 as sort of like a sweet spot. And till today, about 35 years ago, it has changed maybe from 32s to 64, and that's kind of it. So that optimum is pretty flat. Okay. What we're going to do is in these MIPS architecture, we're going to call these groups of 32 bits a word. Okay. The reason is that 32 bits will fit in that register. Each of these 32 registers has 32 bits. And so when we manipulate the data, we're going to say, regardless of where we get the data from, we're going to say this is a 32-bit word, and when we grab it, we're going to place it in that register and kind of fill it up. We'll see later that we'll be able to use smaller chunks of data to do the same thing, but then we have to be careful where in this chunk of 32 bits in the register, where do we put that smaller chunk of data? But nominally, by default, we're going to say, okay, we grab a word and we populate the whole register with that word. Okay. Now, with 32 registers, we could just call these registers, 0 to 31. And depending which school you go to, you may be more inclined to call things with letters or numbers. And so here, we're going to call these registers by name, actually, because it's kind of easier to remember, especially because some groups of these registers, we would want them to have some special functions. When we write code, we want to kind of partition these registers so we can more easily write code like C or directly translate C to this. So the first thing we could do is we would add these like $0 to $31 so to make it a label. But really, we're going to attach these character designators to them. And for example, we're going to call registers 16 to 23 kind of saved variable registers. So this S in front will remind us that this is sort of, these registers will store values that are sort of like variables in C. So whatever I use as a variable in my C program, or I would want to use, I will actually have it here stored in one of these S registers. Okay? Then registers 8 to 15 will be another 8 registers. We're going to call them T0 through T7. And these T will be essentially for temporary variables. Temporary variables will be something that's an intermediate computation that I don't really need, but I need it just for now, and then later I'll kind of do some more computation and produce a value that I want to actually store, right, back into my C variable. Okay? And then later, as we go through MIPS, we'll actually be kind of revealing some of these other names as we need them for these other functions, for example, than arithmetic. I strongly suggest you use kind of the names to make it more readable. People will not really like if you know they get a code from you, even these like small example codes where you just go $0, $7, $15, etc. Because every time they have to look up and check, did you really use the saved variables register, temporary, things like that. Okay. As I already mentioned, kind of in C and higher level languages, you would just go and declare type of the variable, go declare the variables, maybe do even the assignment at that point in time to a variable, whether they're ints or characters, whatever. Later in the code, when you use these variables, the type checking will help you not screw up, right, and do the right thing. And even if you kind of made a mistake, compiler will warn you. You're trying to assign a character to an int. It doesn't work. Okay, so it's not going to compile and let you go further. And so that helps you kind of debug your code more quickly and write correct code. In assembler, in MIPS, all bets are off. You have to be really super careful what you're doing, because each variable is a number of bits, essentially, in the register, right? And so in MIPS, the type of operation you do on the registers will determine which variables you really thought should be used, right? Because otherwise, there's no other mechanism to check. There's no types, essentially. So you will, by typing the instruction, and we'll see later, there are unsigned adds and for example, signed adds, and that will kind of tell you as a programmer, okay, I know how this instruction is going to treat this data. But otherwise, there's nothing else checking that you kind of did the wrong thing. Okay. So let's do some examples. Let's make a calculator. Okay? For a calculator, you need at least the very basic to do adds and subtracts. And kind of first computers kind of did this as well. So to do that in assembly, we will sort of have this very simple instruction. And notice as we go through these instructions, you'll see that MIPS follows like a very, very rigid instruction format. There is here the name of the operation. This is the target register to which the operation gets stored. These are the registers for the operands. So if we looked at this code, in MIPS I would write like this. So add $S0 for the target register, S1 for one operand, S2 for the other. In C, that would just be A equals B plus C. Right? A will be read from S0, B from S1, and then C will be read from S2, or will be stored in S2. Okay? Now, a subtract in assembly will kind of do the same thing. It has the same order. Instead of the add operand, we use the sub. And then S3, again, is the target. That's the same as D. S4, same as E. And then S5 would be the same as F. Okay, so now we have a calculator. We just type this in assembly, and that's it. Now, how do we do this? In C, it's one line. Oh. What do we do here? Any ideas?
Compose addition and
Okay, so the idea is decompose, right? So we can do pairwise addition, and then we do the final subtraction, because I only show you how to do the add with 2 operands, right? So that's exactly what we're going to do. So if you break into multiple instructions, let's say the first one will be add, and then notice this thing, okay? We have S1, so the S registers will be assigned to our variables. So let's say S1 will be B, S2 will be C, S3 will be D, S4 will be E. But I'm not going to assign this temporary add, so B plus C, I'm not going to assign it to any of the S registers. Okay, because the S register is sort of my program variable. But this is an intermediate kind of temporary computation. So I'm going to actually assign it to kind of a temp, and that will be one of the T registers. So in this case, let's say it's $T0. And then I'll keep going. So I'm going to do then T0 with S3. So that will be, this is T0 now with D. And then the last one, subtract that T0 from, or S4 from T0. Right? So that will be this piece over here. So, yeah.
Yeah, I was just kind of wondering why you needed like a subtraction or like even later like a multiplication or division. Why couldn't you just do them all like with addition?
How would you do it? So the question is why don't we just use the addition?
Like the opposite.
So how would you create an opposite? So there will have to be, it's a great question. So the question is like, why don't I just create second complements, right, of the thing and then just keep adding? Because I could take a number, do a second complement of that number, and then add them, right? That's with ints, right? So for that, here I would need kind of to complement it, right, and add 1. And that will be a few more instructions. So because subtraction, again, happens very frequently, I would want to implement hardware support for subtraction. So when I read that the instruction code is sub, my hardware already does that automatically, and I don't waste reading another instruction and then pushing it through the CPU. So that's been recognized as a frequent enough case that if I have it handy, I better use that than pay 3 instructions to do the subtraction, right? So great question. Yeah. No. Okay, that's a great question. We're going to revisit that. So the question is, what if you need 33 variables? I have this long expression as 33 and it's just not cutting it, right? We'll actually see that in a few slides, how we can have 3,300,000 variables if we want to. But we obviously cannot store them all in the register, so we have to go somewhere else. Yeah. Yep.
In this example, instead of using the temporary register, T0, could you just use S0?
You can, in principle, nobody's going to stop you from using it, but you will have enough things going on in the program that you would want to use the variables that are in your code stored in these registers. For example, so the question was, why not use S0 instead of T0, right? So imagine I had some more variables in my code. If I used S0, I would be overwriting that variable, right? And then later, maybe some other expression would want to use that S0, but I wouldn't be able to use it, right? So if you have enough space, you could, but this way we partitioned S0 and S and T registers so that you can kind of have some space for the temporary variables while still preserving some of the saved variables from the code. Any other? Okay. So the point here of this expression is that you see that one simple line of C actually may take multiple MIPS lines in order to execute. And we'll see this is not only the case with adds and subtractions and like expressions, but when we go into loops and decisions later, as well as the function code. There will be some tasks that we just need to spend several more instructions in MIPS because it's not as efficient. You have to kind of compose a bigger task out of many smaller chunks. So this, we talked about the temporary registers. One actually Yeah, so one point here is that we use this hash, and then I was explaining kind of what the thing does. Assembler would just ignore this, right? So just like a comment mark in C, we could actually use hash here to denote anything. And believe me, when you write the elaborate assembly code, these comments will become very handy for you to go back and later understand what the heck you did. Okay, so or anybody else. So strongly recommend doing very, very generous verbose commenting there. Okay. There is another thing we often do. In fact, if you look at profile the codes, like for example spec, int, or like these types of benchmarks, very frequently we actually use a constant to do something in the code. And having an instruction, then again, that supports doing that will actually save you quite a bit. Because imagine, as we talked about, that you cannot fit everything in these 32 registers. For that number, you would have to actually go and fetch a constant from the memory, and we'll see that's actually very, very slow. So rather than doing that and spending instructions on getting just a constant number from somewhere, you might as well embed it in the instruction itself. And so that's what we exactly are going to do with these, what we call immediates. The reason why we call them immediates is because they are already in the instruction. Right? So remember the binary code that I showed you at the beginning, where we kind of translate a simple MIPS instruction into ones and zeros. Well, some chunk of those ones and zeros will be actually that constant that we're going to use in computation. Okay, so for example, when we do something like this, an add with a constant will be just our add tag, but we're going to have this I for immediate. So that will say that you're actually adding a constant, which is in this third field, in this case it's minus 10, to this register S1, and then storing that value in register S0. So in this case, S1 will contain the G variable from C, from this expression F equals G minus 10, and then S0 will contain F. This minus 10 will be stored. If you look at this, it's a one-line MIPS instruction, and as such will be translated exactly to one line of zeros, 32-bit zeros and ones. So that number minus 10 will actually be part of that string of bits. And so when you execute instructions, by just reading that instruction, you already got that number. You don't have to go to memory and get that number. Right? So that's sort of the speed advantage of these immediates. Okay. So again, it's kind of the argument is kind of embedded in the instruction. Now, there is, question.
Is there a size limit on the immediates? Like, can you go past 256?
I don't know exactly. What? 16 bits? Yeah, 16 bits. We'll see later in the instruction formats. This is what you get. But these are signed and unsigned, right? So you can go up to 100, half of that whole range. Now, there is one special constant that is used like a ton, above all the numbers. Does anybody guess what that is? Zero. Yeah, great. So it's so special that you actually want to dedicate a whole register to it. Okay? So what you're going to have is you're not even going to have like add intermediate and then kind of the number. We're going to have this register, actually $0, which is your zero register, is going to be hardwired to contain all zeros. Okay? So we're going to call it in this code $0 with 0 in text. So to just make sure people don't confuse it with a 0 and S that somebody forgot or something like that. So this is going to be a 0 register. In this case, this add really just does the assign, like of G to F. Right? Okay. Here's a little reminder. When we talked at the first lecture, and kind of a little bit about in the second lecture about number representations and addition, right? With signs versus unsigns. there was this issue of overflow, right? Overflow was this event that happened because we only have a fixed number of bits in which we want to represent a number. So we, for example, have two positive numbers, and when we add them, that sum is outside of this range that we can use to represent the number. We're going to get a negative number. Right? Let's say, take a look at this example here. If I'm using only 4 bits to represent the numbers, then when I do all ones plus 0, 0, 1, 1, I'm going to actually get this 5th bit. Right? And so instead of getting here a number of 15 plus 3, which is these two unsigned numbers, instead of getting an 18, I'm actually going to get 2. Because I'm not even going to see this bit. I only see the lower 4 bits, which is obviously wrong. So something needs to react in the system saying, wrong, I hope my wallet was increased by $3 and not like decreased by 13. So something needs to happen, and usually different systems react differently. On computation, they throw an exception and say something happened here. We detected an overflow. Some languages can detect this when they're compiling and make sure that the underlying hardware can deal with it. But here's sort of like a little map how things get handled with these MIPS instructions. Right? So in some languages like Ada or actually Fortran to MIPS compiler, you'll actually be able to carry over that type and overflow checks. But MIPS has kind of 2 types of instructions. If you write your MIPS code directly, if you write add immediate, and subtract, those are kind of the instructions we already covered, then MIPS will actually, it will cause the overflow to be detected, and MIPS will throw an exception, and there's going to be sort of the exception routine that will handle this exception. Okay. Now, if you use the unsigns, so these are going to be just add, and then there's this letter U for unsigned that's appended to the instruction name. That tells MIPS you're working on unsigned integers, right? Which usually you will be doing when you kind of do the address increments and things like that. Add immediate also when you're incrementing the address with a fixed kind of constant, subtract, etc. And MIPS will actually do nothing here to detect the overflow. Okay? And actually, C compiler to MIPS will turn all your adds and stuff into actually these unsigned operations. Right? Adds. So there will be no kind of overflow detection. But you don't have to worry about that necessarily here in the course. This is just to give you an idea what's happening under the hood. Okay. There was this question earlier, a great question actually, about what do we do if we have more data, more variables than we can actually fit. So you see, here's the CPU, the processor. Here's the arithmetic logic unit. That's where all the adds and subtracts happen. Registers, we want to place them right next to that unit, right, on the chip. There's only 32 registers, so if we need more data, we will have to actually go outside the chip to the memory and go fetch that data. Now, in modern processors, this is not exactly what you're going to see. All right? You're going to see a memory hierarchy, a number of different memories of different sizes that will kind of bridge this gap. Okay? This gap here, we talked about light hitting the wall in 30, 40 cycles of processor. Well, we'll see later that going to a real big memory like DRAM will take, again, 50 to 100 cycles. And so you don't want to sit idle and do nothing while that's happening. You want to be able to introduce some other memories in which you may have a higher chance of getting that data from. So they're neither, again, Goldilocks thing, right? They're neither too small or too big. They're somewhere in between, and you have some chance of getting your data from it. That's called caches, and we're going to talk about that In your normal processors, you have L1, L2, L3 cache. So 3 times the chance, three times the charm, so you have 3 shots of getting your data before you have to take that long trip. But each time you hit a bigger memory, it takes more time for you to get that data. So there's some trade-offs there. Okay? So what's important on this chart, just for people to get the reference when we talk about things. So everything is kind of with respect to the CPU, right? Write data stores data to memory, right? And then you kind of read data, you're loading from the memory. So from the memory to the CPU. Right? And so that's what we're going to use load and store commands in MIPS. So store would mean store to memory from the processor. Right? Not store to the processor from the memory. And then load will be load from the memory to the processor. It's the word I want to work on. And once I'm done working on it, I'm going to store it back to memory. So just get this kind of concepts, because we're going to use them a lot. And then, again, our program is not going to be a few lines either, right? So we will have to actually store the program itself in the memory. And again, because we want to do things fast, we will also have kind of instruction cache, which is our little memory on chip that will store some portion of the program, and then we're going to be getting some more as we go. Right, we're going to kind of talk about that. So in memory, you hear kind of like, okay, my laptop has 8 gigabytes of memory, yours has, or my phone has 16 or 10. So byte is kind of a chunk of information. In these cases, we refer to it as 8-bit chunk. Right? 32 bits for a lot of things is just too much data. If I work on characters, I'm not going to want 32 bits. I want to operate on smaller chunks of data. And so people throughout the years have sort of looked at this 8-bit chunk of data, name it byte, to be sort of the smallest useful chunk of data that one would use. Nibble is kind of half a byte. Sometimes that's useful too, but really a byte is something we want to kind of look at. And so we say our memory has, let's say, 8 gigabytes. But we can fetch that byte from the memory, but because that operation is kind of expensive, usually you fetch more. Okay. And because we have 32-bit registers in our CPU, instead of going and fetching a byte at a time, which we will also have some instructions for, just in case, we really will go and just fetch a whole word from the memory. Right? So one word is 4 bytes. Right? It's 32 bits, is 4 times 8. Now, memory addresses are really in bytes, right? So for me to fetch the word, I actually have to increment the memory not in increments of 1, but actually increments of 4, right? So the way memory is going to be organized is sort of like this, right? Where you start from, in this row represents 32 bits, right? So 4 bytes. In MIPS, this is something for you to kind of remember. We named these bytes 0, 1, 2, 3 from left to right. Okay, and that's called big endian. Okay? There are machines that are called little endian, and those machines start numbering from 0 here. They go 0, 0, 1, 2, 3. So if you're using byte load instructions, or just even loading the whole word, you want to know from where you're starting. So in MIPS, 0 will kind of mean the address of the leftmost byte in the word. Okay? And then 4 will be the next word. So when we go here, we want to fetch this next row, which is 32 bits. The address of that word will be 4. Right. Okay, any questions about this? It's kind of a tricky one, yeah?
So is this like a pointer to an array or something like that? Or?
Exactly, and we'll see, yeah, so the question is this a pointer to an array? Exactly, it's because of the address of that word in this memory array. And we'll see which instruction, in the next slide, which instruction we're going to use to do that. So now we're doing transfer from the memory to the register, right? So what instruction are we going to use? What's the name? Load, right? We said from memory to the registers, we're loading from the memory. So we're going to use load. And so let's say we have this C code. We have an array. It's a 100-element array. Obviously can't fit in our registers, right? And I want to do a computation where I increment G, which is my C variable, or my H, by a third variable in the array. Third integer, or fourth integer in the array. Okay. So we're going to use LW. LW will be a shorthand for load word in MIPS. Right? And so the way we're going to use it is sort of in this format. So it's load word. T0 is going to be our temp register. And this register will get this value A3. And here's how it will get it. We're going to use S3 as a pointer. Right, so the content of the S3 register will be a pointer to the beginning of this array in the memory. So remember in the previous slide I showed row 0, row 4, etc. So that address, 0, 4, 8, 16, etc., so that memory address will be the content of this register S3. And then we're going to add an offset to that content. In this case, we're adding an offset of 12. Okay? This offset is in bytes. So does anybody know why we're adding 12 bytes of offset to the base? Base points to A of 0, right? A of 0 is my first integer. It's a 32-bit value, right? So it's the first integer in the array. Why are we adding an offset of 12? Yes?
You have to add the size of 3 words.
Okay.
4 bytes each.
Why a word? So the answer was you have to add the size of 3 words. So why a word? Yep.
It just so happens that ints are the same size as a word. And int's 32 bits.
Yeah, so the answer is int is 32 bits. It is exactly the size of my word, right? So for me to go from A of 0 to A of 3, right, I have to increment my base by 3 words. And each word is 32 bits or 4 bytes. So my increment, my index here, 12, is in bytes. Right? So I have to increment by 4 times 3, which is 12 bytes. Make sense? All right. This is the single most critical piece in kind of MIPS programming. You don't believe how many people will do this calculation wrong and will put an index of 3, for example. Right? Forgetting that byte addressing is different from word addressing. Right? And you need to look at what is really the thing you're fetching, what's the size, and by how much you really would want to jump that array. Okay? So after we got that value, A of 3, it's in the temp register because in my code that value it really is not kind of the variable, right? It's just a value I want to use temporarily. So I store it in T0. And then once I have it, then I'll just do a normal add between T0 and S2. Variable H is stored in S2. And I'm going to get my variable G, which is stored in S1. Okay? So again, S3 is we're going to call it sort of the base register or the pointer into the array. So if our array was A of 100, so at A of 0 is really kind of the value that is stored in this register S3. So whatever we have in that bracket, you better make sure that the pointer to the array you want to access is in that bracket. Okay? And then 12, again, is the offset in bytes. So we have to very carefully calculate by how many bytes we need to jump in order to address the next element in the array. That again depends what is our array. Is it int or is it char, right? Or things like that. This offset of 12 is not a variable. You cannot go and put a variable, like another register here, like $S1 in the bracket $S3, because that offset needs to be known at compile time. Okay, so let's do another example. Transfer from register to memory. We use which instruction? Store. We're now storing stuff from the registers to the memory. Again, we have the same code. Now, instead of G, we actually want to modify A of 10. So we go grab A of 3, add it to H, and then we go and store that in A of 10. So, can anybody tell me what offset am I going to use to store to A of 10? Hmm? 80? Why? So the one answer is 80. Why 80? What offset did we use for A of 3? 12, right? So what should we use for A of 10? 40. 4 times 10. Because 4 bytes is in a word, right? That whole word I'm counting 0, 1, 2, 3. Then the next word is 4. 4, 5, 6, 7. Then the next word is 8, 8, 9, etc., right? Okay. So that's what we're going to do. First load, we know that. We're going to add. Okay, that's all the same as before. And now we're going to store. And again, in this store, this value that we computed that's in T0, that was our H plus A of 3. Now we're going to store that value into the base incremented by 40 bytes. Okay, that's now my A of 10. Okay, and now I get value T0 stored in that location. Yeah? Nothing. You will overwrite it sometime. I mean, you don't lose the value. It's still in the register. And if you can, any other piece of code down there, like any other follow-on instruction, will probably use it for something. Usually registers, depending how it's done, you will sort of physically overwrite the register with something you want to. Yes? Yes? Question is S3 a pointer to a register? S3 is a register itself, okay, that contains a pointer to some location in memory. And in this case, since we're operating on the array, it will be a pointer to the base of the array, like ampersand A of 0, right? That was our base of the array. Okay, yes?
So if our type was like 16 bits and not 32 bits, would we use 1 instead?
Type was 16. Yes, you would have to kind of decrement. You will be able to, on a load, you would be getting 2 elements, right? Then you have to do some masking to figure out how to access each one. Actually, so the question was, if it's 16, do you half the offset? You do, because you will be able to get twice more elements within a certain range. There are other instructions called LH, load half, and LB, it's load byte, with which you'll be able to do that exactly, right? So I'm showing you load word. But if you look at the MIPS sheet, and we'll have a few examples on that too. Not on load half, but LB. Okay, so again, here we had a base, and then our offsets were 12 and 40, which are multiples of 4, okay? So that we could access the 3rd and the 10th element in the array, because each element is 4 bytes. Okay? Now, just remember this, whenever we're doing LW operations, $S3 plus $12, that whole address, right? So that value of the address that we're looking for the word has to be a multiple of 4. Remember, we're storing words in memory beginning at addresses that are multiples of 4, 0, 4, 8, etc. So if my total word address is not a multiple of 4, I'm byte misaligned. Okay? Means like I'm starting from like a second byte in the word, getting 3 bytes, and then another byte of some other word. That's not really good. I'm going to get some junk. Okay, so this is a quick check for you when you write your code. Whenever you're using LWSW, the sum of these two, of the content of S3 and the offset, or here again, has to be a multiple of 4 when you're using load word. Okay, so a quick example on, there was a question about what if you're seeking something that's less than a whole 32 bits. So there are these instructions LB, load byte and store byte. Now these, because byte is really the smallest unit I can address, the address for that can be whatever, right? Whichever number. It doesn't have to be a multiple of 4 because it's just that exact byte that I want for whatever reason, okay? It's same format, so you will have again LB, S0 will be the target register to which you're going to load. You're going to load the content of S1 plus 3, that address you're going to grab from the memory, so that byte that resides in that address. Now, the trick is, where are you going to load it? It's a 32-bit register, and you only got 8 bytes, right? So this LB will load it into the lowermost byte in the register, and then it will actually do assign extend all the way. So if this is my register, these are the 8 bits that I loaded from the memory. We'll take this sign bit and sign extend it all the way. So that's what LB is going to do. LBU is going to do what? Anybody guess? Unsigned extend, so zeros, right? So we'll not sign extend. Right? So if you don't want the register to be sign extended, use LBU. If you want to have it sign extended, do LB. Okay. So we already talked about this. That registers are small. We only have 32 words, so not a lot, 128 bytes that we can work on. They're very close. Memory will be 2, 8, 16 gig, 192 if you have a big server, and do some interesting chip design. And then, but the risk principle is smaller is faster, so we're going to not grow that number of registers on a chip much. We already talked about that going to memory, just because of this speed of light kind of thing, and some other things, it will really be 100 to 500 times slower than really going to that register. So we really want to minimize kind of when we need to do that. Okay? This is my first time using clickers, so I'm going to give you an easy question. Okay? Okay, I'm going to start the poll. Please don't put E. Save E for next week. Okay, seems like we're kind of saturated here, so I'm going to stop it. Okay. Woohoo! Okay, so this is pretty good. As I said, and I wanted to kind of mention that at the Administrativia thing, but I mentioned again there, homework 1 is out, and so please get started. Let's do this, unlike homework 0, which you had 2 weeks for. This is like only 1 week. It's due on Sunday, and there's a lot of work to do. So please get started. Okay. Okay, this was an easy one. Here is a little bit harder question, but should be still very easy. So I'll let you first kind of, well, let me open it up. Think a little bit and then just do it yourself, and then we're going to do, we'll have a couple of minutes to discuss and then do it again. So maybe let's do this like in a minute and a half or so. Please, by yourself, so that you'll have some chance later. Let's just check your own kind of understanding. Okay, so it looks like numbers are saturating. We're going to stop it. Okay, so ready? So at this, so two contenders, right? Why don't you talk to your peers a little bit, and let's say a minute. We're going to do it again. Okay, let's get a few more votes. Let's get a few more votes in. So we gotta, yep. We want to get above 300. Come on. A few more. Okay. Okay, here it is. So, what we have here is, so in C, we have a load word. So we're loading into a temporary register the content of the word in the memory that's pointed to by what is in S1. So S1, what is in S1 is really a pointer to that memory location, right? So, and that kind of fulfills this thing that Y is a pointer. It's in S1. So then we're looking to grab a value for that pointer is pointing to, right? We don't want any offset because that's exactly the location in the memory where we want to grab stuff from. So offset is 0. Then we do add immediate because we're adding a constant, right? So add immediate uses this temporary 0, which is where our star y is stored. Now, and then adds a 1. And then we do a store word now from the register T0 to the memory. Again, we're computing the memory address to store to by looking at a pointer which is in register S0. That's our X. It's in S0. We add 0 as the increment because that pointer is exactly where we want to be in the memory. And then we store T0 there. Right. I'm not going to go through some of the silly answers like this one where it's just a confusion between load and store kind of direction. This between base. But this one maybe is worthwhile talking a little bit about. Some people maybe selected this because of the confusion about what the pointer is, right? Or what star X is versus just X. So X, it really contains the address where we want to store that value in the end, not the value itself, right? So we cannot adding to X means we would just change the address where we want to store by 1. We would move it out of where we really wanted it to be. Right? Okay. We have a bunch of things to kind of go into. I'll go as far as I can do it, and then we'll continue in the next class. Apart from these, so what we did so far were kind of some of the arithmetic operations, right? Add, subtract, signed, unsigned. Then when we ran out of registers, we kind of used load word, store word, load byte, store byte to kind of fetch some more. But we'd like to do some other things as well. And part of the whole MIPS ISA are also these logical instructions. Logical instructions allow you to do bit-by-bit logic operations. So take a 32-bit word in one register and another 32-bit word in another register, and you can do bitwise logic operation. For example, bit-by-bit AND, which is very useful when you're trying to create a mask of bits that later you can use to modify only a select portion of the whole word for whatever reason you want to do it. Let's say you want to operate only on some byte in the word. You'll first create a mask that kind of covers with ones just that piece and then do operations on that. So some of the here are AND, bit by bit OR, bit by bit NOT. That basically inverts every bit. So we talked about possibly inverting stuff and then adding for a second complement. So you could use that. Shift left and shift right will be SLL, SRL. SL is for shift left. This thing here says shift left logical. And we'll see what the difference between that and kind of the arithmetic. So shift right logical instead of arithmetic. So we're going to see what those differences are. So in logic shifting, the instruction will go something like this, like SLL, S1, S2, 2. And what this would mean is that S1, which is always our target register, receives S2 shifted by 2 bits. Okay, shifted left by 2 bits. So if I shift left by 2 bits, what comes into these other 2 bits? Anybody have any idea? Zeros, right? In the shift left logical, we would insert zeros on the right. So if we had a number that looked like this, 0002 hex, means binary, it would be this, with this 1 0 in the end. When we do SLL by 2, we're going to insert these 2 zeros right on the right side. What operation is this equivalent to? What arithmetic operation? Yeah, so the answer is times 4, right? We've turned a 2 into an 8. Right, so 2 is here, now it's 8. So shift right, logical, will shift the whole word right and insert bits from the right. What bits? Anybody? Zeros. Right. Now, zeros wouldn't really kind of care about what was the sign of that number that you were shifting, right? Remember, this is done on registers. You could have a signed or unsigned number in that register. MIPS doesn't care. It will do happily this shift right logical and mess up your number if it was sort of a signed number, right? So for that reason, it is arithmetic shifting, where if you're shifting right by n bits, you want to preserve the sign, right? And therefore, you would kind of do this, for example, minus 2510, 2's complement will be this. And then when you do the shift, let's say we do this instruction, SRA, shift right arithmetic. We want to store in the same register its own content, but shifted by 4 to the right. Right? So we would get a number like this. Now, keep in mind, we would actually preserve the sign here as we're shifting. Okay. Fortunately, this number is not going to be the same as dividing by 2 to the n, right? Because in C, the arithmetic semantics of division should kind of round up towards 0. So you got to be careful when you do these things and relying that it's actually going to give you a divide operation. Okay, we're going to, in the remainder, just start on computer decision making, because what we've done so far, we kind of built a calculator, right? The thing so far that you know how to do in MIPS is add, subtract, do logical operations, store, read from memory, so you can do it on any number of numbers, right? So your expressions could be million variables long. You could do it, but you can't do anything else. The calculator has no decision power. If it's faced with kind of some logical expression, it won't know based on it to take left or right, right? And execute some code and not execute some other code, which is kind of the key to intelligence, right? So which instructions in C we had to kind of do that? Provide us with program control. Anybody? We could do it add, subtracts in C too, but there were some other things that we did that allow you to kind of control how the flow. Yeah. Yeah. If, for example, even if would be great, right? If else is even better if you have something else to do, right? There's more complex constructs like switch, right? That's if you have multiple choices you want to address instead of doing nested if else kind of things. What else can you build if you have if and else, but you need kind of some repetitive action? What? Yeah, you can build a loop, for loop, while loop, any other loop. do loop. Yeah, those are the 3 types of loops we want to support. So we want to be able to do all this same stuff in MIPS too, right? Because that will give us the most flexibility how to translate these C programs to this. Okay, so again, in programming languages, we would use if statement or if else. In MIPS, we will, in the most kind of rudimentary MIPS, we would use branch if equivalent. So, and what this instruction does, it compares register 1 with register 2. Did I have register? Yeah, okay. Register 1, register 2. And then, if they are equivalent, it will jump, okay, to this label L1. Now, what is L1? Let me see if I have an example here. Okay, I don't. We have it on the next slide, but every MIPS instruction, in front of it, you can put a label. Okay? Label colon and then the instruction. This really is just for humans to kind of know what is where in the code. Every line of MIPS code will actually have an instruction address associated with it. Because as the program is in the memory, you will be going from one instruction to the next by going from one instruction address to the next. We'll see later how that happens. But for us humans, we don't care about these numbers. You don't use all of these addresses of instructions, but you want to maybe occasionally jump to a particular place. And so you will, somewhere else in the code, label some instruction, L1 colon, that instruction, and this branch or equivalent will actually take you there if this condition is true. Okay? So this means like go to and then a statement or instruction that is labeled L1 if the value of register 1 is equal to value of register 2. Anybody programmed in BASIC, there was these go to instructions. Yeah, okay, okay. Except for me and Krista, maybe. Yeah, okay, there's some more takers. So yeah, BASIC would have this. I think as Dan would call it in previous classes, you can also do this in C, what we call stank C. For C that stinks, because it's really, go-tos are really bad. You have to kind of track where you jumped and how then you're going to pop back from there. But in MIPS, it's kind of a necessity. There's no other construct to do this kind of branching except to jump and do stuff. And as we'll see with functions as well, you're going to have to jump, do some stuff, come back. Okay, so we're going to have this branch if equivalent. Now, if you don't jump, you don't branch, you will just go to the next statement. So if my code has multiple lines of instructions, after BEQ, if the condition is not true, I'll just continue. Okay. This stands for branch if equal. Sometimes that's not the condition I want to test. I want to test if it's branch if not equal, right? And because that also appears very frequently, and there's another instruction called BNE, branch if not equal. Okay? So here's a few types of branches that we're going to cover. So again, branch is kind of a change of the control flow. I'm going through my instructions one by one, and all of a sudden, based on some condition, I don't want to execute the next instruction, so I jump. Right? And so I change my control flow. So this is called a conditional branch. Right? We're going to jump somewhere or not jump, depending on some condition. And what we covered so far is branch if equal or branch if not equal. That sort of covers the equalities and non-equalities. Or equalities or when one thing is not equal to another. But if I have inequalities where something is smaller or bigger, I need a separate instructions I'm going to show you. We also have unconditional branches. At some point in the code, I just want to jump. Okay? And there can be various reasons for that. I figured I completed my code and I just want to jump out of there. If it's a function, I complete a function, I want to jump back to where I was. No conditions. I'm done. I want to jump back, right? So there are these functions, and it's what we're going to use here. An example is jump or just J. That's kind of the instruction label we're going to use. So Here, let's do an example for the if statement. Actually, I'm going to stop here real quick. I think you deserve some news. And then but before I do that, there was someone who wanted to do a 30-second kind of advertisement. Yeah, why don't you do it when I do this?
Next week is Vagina Monologues. It's February 12th, 13th, and 14th, Thursday, Friday, Saturday. Tickets are being sold right now, all week, and next week until we sell out, which we usually do. It's at Wheeler, 7 p.m. Vagina Monologues, if you don't know, is a production put on every year. We have different pieces that all target gender issues such as gender-based violence, being a woman, being a trans woman, etc., etc., etc. It's a really good show. It's a great platform for discussion on gender issues that are relevant to any space, including this one. So it would be really cool to look them up and support. I shaved one armpit for this.
Okay, 30 seconds up. 30 seconds times 4. Okay, I just wanted to give you a little bit of piece of news about MIPS before we disperse. MIPS is actually in space. You know, in July this year, it will actually pass past Pluto and take some snapshots. There's 4 MIPS CPUs on that craft. It's been launched 8 years ago, or almost 9 years ago. And actually, these chips that you see here are called rad-hard. They're on SOI substrate so that radioactive particles cannot screw up the computation. So, yeah, you have the site here so you can check it out. Pretty much everything on this craft depends on the MIPS. Guidance and control, which is very important. Command and data handling, you know. So if you kind of learn MIPS, you'll kind of know how to program the spaceships. Another thing I wanted to point out is the administrative stuff. Please, hopefully everyone turned in homework 0 and didn't use their tokens on that easy homework. This one is due on a Sunday. Please get started, okay? And we'll do the branches next week. Thanks.